Hello everyone, today I will introduce the topic of nuclear fusion. Nuclear fusion is a process in which two light atomic nuclei combine to form a heavier nucleus, releasing a very large amount of energy. This process commonly involves hydrogen isotopes such as deuterium and tritium which fuse together to produce helium. Nuclear fusion is the same reaction that power the sun and other stars. It follows Einstein's mass energy equivalent principle where a small amount of mass is converted into a significant amount of energy. However, fusion can only occur under extremely high temperature and pressure, allowing the nuclei to overcome their natural repulsive force and fuse together. Because of its potential to generate clean and abundant energy, nuclear fusion is considered one of the most promising energy sources for the future. Now, I will explain the importance and significance of nuclear fusion in modern physics. Firstly, compared to fossil fuel, fusion energy is much cleaner and produces very low greenhouse gas emission, making it a more environment-friendly energy source. Secondly, research in nuclear fusion contribute to advancements in plasma physics, particle physics, and other scientific fields. This study helps scientists better understand the fundamental law of nature. Thirdly, fusion research drives the development of advanced technology, including superconducting magnet and high temperature material that can withstand extreme conditions. In addition, successful fusion technology could help reduce global warming and decrease our dependence on non-renewable energy sources. Finally, many countries continue to invest in large fusion projects because fusion has the potential to provide a sustainable, reliable, and long-term solution to future energy demands. Next, I will explain the methodology used in nuclear fusion research. The first method is magnetic confinement fusion or MCF. In this approach, hot plasma is confined using powerful magnetic field inside device such as a tokamak or a stellator. The main fields used are deuterium and tritium. The objective is to maintain stable high temperature plasma for continuous energy generation. The second method is inertial confinement fusion or ICF. In this method, small fuel capsules are compressed and heated by intense laser beams from multiple directions to initiate fusion. One well-known example is the National Ignition Facility. The goal is to achieve fusion ignition through rapid field, compressed ion, and heating. Finally, research are also exploring emerging and alternative approach, including compact fusion reactor, Z-pinch system field, reverse configured ion, and magnetic target fusion. This approach aims to make fusion reactor more compact, efficient, and cost-effective in the future.
Assalamualaikum and hello everyone. In this section, I will explain the concept and law behind nuclear fusion. First, let's look at the nuclear fusion concept. Nuclear fusion occurs when two light atomic nuclei combine to form a heavier nucleus. During this process, a tremendous amount of energy is released. This happens because a small amount of mass is converted into energy. Fusion naturally takes place in the sun and other stars, making it the primary source of the energy. As shown in the diagram, a deuterium nucleus and tritium nucleus fuse together. The fusion reaction produces a helium nucleus, a neutron, and release a large amount of energy. This is known as the fusion reaction process. Next, let's discuss the mass energy equivalence law. This law was proposed by the famous physicist Albert Einstein. It states that mass can be converted into energy according to the equation E equal to mc square, where E represents energy, m represents mass, and c represents the speed of light. This equation explains why nuclear fission can produce such a large amount of energy. Even a very small loss of mass can be converted into an enormous amount of energy because the speed of light squared is extremely large value. Now I will explain the importance of nuclear fission. The first importance is enhanced energy security. The widespread availability of fusion fuel can reduce our dependence on imported fossil fuels. As a result, countries can strengthen their long-term energy security and become less vulnerable to fluctuation in global fuel price. The second importance is high energy output. Nuclear fission can produce an enormous amount of energy from a very small amount of fuel compared to conventional energy sources. Fusion is much more efficient and has the potential to meet the large-scale energy demands. The third importance is support for future global energy demands. As the world's population continues to grow, the demand for electricity and energy also increases. Nuclear fission offers a promising and sustainable solution to meet future energy needs while ensuring a stable energy supply for future generations. Now I will explain an example related to nuclear fission. First and foremost, the first example is International Thermonuclear Experimental Reactor or ITER. ITER is one of the largest nuclear fission projects in the world. It is an international collaboration involving many countries working together to develop fusion energy technology. The main goal of ITER is to demonstrate that nuclear fission can produce more energy than it consumes. To achieve this, ITER used a device called a tokamak, which relies on powerful magnetic fields to contain and control extremely hot plasma. Scientists and engineers from different countries are contributing their expertise to overcome the technological and engineering challenge involved in fusion research. If the project is successful, ITER could become a major step toward commercial fusion power plants. This would provide a cleaner, safer, and more sustainable source of energy for future generations. Next is inertial confinement fusion or ICF. ICF is a method used to achieve nuclear fusion by compressing and heating a very small fuel pellet that contains deuterium and tritium, which are isotopes of hydrogen. In this process, powerful laser beams are directed at the fuel pellet from multiple directions. The intense laser energy causes the outer layer of the pellet to explode outward. As a result, a strong inward force is created, compressing the fuel to extremely high temperature and pressure. Under this extreme condition, the atomic nuclei can overcome their natural electrostatic repulsion and fuse together. This fusion reaction releases a large amount of energy. ICF is an important area of fusion research because it helps scientists study how fusion can be used as a future source of clean and sustainable energy.
I will explain the daily life application of nuclear fusion. Fusion energy can generate clean electricity for homes, schools, hospitals, and businesses. It can also power electric vehicles and future transportation systems. In addition, fusion energy can support water desalination by converting seawater into drinking water. It can provide stable energy for hospitals, research centers, and data centers, as well as help factories produce goods more efficiently. Overall, fusion energy has the potential to improve many aspects of daily life. I will discuss the advancement and controversies of nuclear fusion. Recent advancements include successful fusion ignition at the National Ignition Facility, improvement in superconducting magnets, and progress in the ITER project. Private companies are also investing more in fusion research. However, there are still challenges such as high development costs, long implementation timelines, and difficulties in achieving continuous net energy gain. Fusion also faces competition from renewable energy sources like solar and wind power. Fusion energy offers many exciting career opportunities. Some examples include fusion physicists who study plasma and fusion reaction. Next is nuclear engineer who design reactor system and research scientists who conduct experiment and develop new technologies. Other careers include energy consultant and material engineer who help improve and implement fusion technology. Work in the fusion industry, several skills are important. A strong understanding of physics, especially nuclear and plasma physics, is essential. Mathematical and analytical skills are needed to solve complex problems. Programming skills such as Python or MATLAB are also useful. In addition, communication and research skills are important for teamwork, experiment, and presenting findings.
Next, I would like to discuss the significance of continuous self-development in the field of nuclear fusion. Nuclear fusion is a rapidly evolving area of science and technology. New discoveries, improved reactor designs, and advancements in plasma control systems are constantly being developed. Because of this, professionals working in the fusion industry must engage in lifelong learning to stay updated with the latest knowledge and innovations. Continuous learning helps scientists and engineers improve reactor efficiency, enhance safety standards, and contribute to future breakthroughs in fusion technology. As a student, I understand the importance of professional growth. To strengthen my knowledge, I actively participate in webinars, read scientific articles, and follow developments from leading organizations such as ITER and other fusion research institutions. By continuously learning and improving my skills, I can better prepare myself for future opportunities in the energy sector. Despite its great potential, nuclear fusion still faces several significant challenges. The first challenge is the extremely high temperature required for fusion reactions. Fusion can only occur when temperatures exceed 100 million degrees Celsius, allowing atomic nuclei to combine. To address this challenge, scientists use advanced magnetic confinement systems such as tokamaks and stellaratos to safely contain the superheated plasma. The second challenge is the high construction and maintenance cost of fusion reactors. Developing and operating these facilities requires substantial financial investment. One effective strategy is to encourage international collaboration and increase funding from both governments and private sectors. This helps contribute costs, share expertise, and accelerate technological progress. By overcoming these challenges, fusion energy can move closer to becoming a practical and reliable source of clean energy. In conclusion, nuclear fusion has enormous potential to become a sustainable and reliable energy source for the future. It offers many advantages, including high energy output, minimal greenhouse gas emissions, and abundant fuel resources. Although challenges such as extreme temperatures, high costs, plasma instability, and material durability still exist, ongoing research and technological advancements continue to provide solutions. Major projects such as ITER, the National Ignition Facility, and inertial confinement fusion research demonstrate the global commitment to advancing fusion technology. With continued innovation, international cooperation, and investment, nuclear fusion could play a key role in
meeting future energy demands while protecting the environment. Therefore, fusion energy remains one of the most promising pathways toward a cleaner and more sustainable world.